Good morning and welcome to the 8th lecture in the course Stochastic Hydrology. If you recall, in the last lecture, we discussed the extreme value distributions, specifically the extreme value type 1 distribution, which is also called as the Gumbel's extreme value distribution. This is generally used for the maximum values. For example, we may be interested in the peak flows, maximum rainfall, etc. Then we also covered the extreme value type 3 distribution for minimum values. This is also called as the Weber's distribution. Recall that we use the Weber's distribution specifically for low flows, minimum rainfall, minimum water quality and so on. Then we went on to discuss the topic of parameter estimation, where given a PDF, we would be interested in getting the parameters from a given sample values. In this we discussed three methods: the method of matching points, where from the available data observations we deduce certain probabilities, for example, probability of x being greater than or equal to a certain value is equal to, let us say, 0.8 or some such thing. And then depending on the number of parameters that you have for the PDF, you deduce various such probabilities. Let us say if you have 2 parameters, you deduce 2 probabilities from the available observations and equate it to the theoretical probability that would result from the use of that specific probability distribution. By equating these, you will be able to get the parameters of that particular distribution. The method of moments, we take those many moments of the PDF as you have the number of parameters. For example, if you have 2 parameters, you consider the first 2 moments of the PDF. The first moment being the expected value of the random variable itself. The second moment you take about the mean, and therefore, you define the variance. In the method of and you generate those many moments as you have number of parameters, solve those equations and then get the parameters from the sample. In the method of maximum likelihood, which we will again review today, you define what is called as the likelihood function, which is based on the sample values x 1, x 2, x 3, etc., x n, and then you look at those parameter values of the PDF, which will maximize this likelihood. So, essentially the principle there is, what is that set of parameters? We are looking for that particular set of parameters that will maximize the likelihood of obtaining the sample x 1, x 2, etc., x n, which has in fact been realized. That is the idea there. So, in the maximum likelihood method, we define the likelihood function as f of x 1, theta 1, theta 2, etc., theta m, where theta I are the parameters, into f of x 2, theta 1, theta 2, etc., theta m, and so on until x n. So, this we define it as multiplication of f of x I, theta 1, theta 2, etc., theta m. Then we look at those parameter values theta I, which will maximize the likelihood function thus defined. So, we maximize the likelihood function with respect to theta I. So, we take the first derivatives of the likelihood function with respect to theta I for all I, equate them to 0, thus generating m equations. We solve these m equations to get the associated theta I values. That is the principle of the maximum likelihood function, maximum likelihood method, I am sorry. Let us consider an example. In the last class, we discussed one simple example of the exponential distribution, which has a single parameter lambda. Now, we will take another distribution which has a single parameter beta. The PDF is given by 2 beta root of beta by pi x square e to the power minus beta x square, which is defined for x varying between minus infinity to plus infinity. So, we formulate the L of beta. Remember, we have a sample x 1, x 2, x 3 etcetera, and we are enumerating the PDF at those given values of x i's, and then taking the product of these f of x is defined over defined at that particular x I, and then we are calling that as the likelihood function. So, we define the likelihood function is equal to 2 beta into beta by pi x 1 square into e to the power minus beta x 1 square into etcetera. Like this, every time we change the x value to x 1, x 2, x 3 etcetera up to x n, and then define the likelihood function. So, you have n terms here. So, this will be 2 to the power n, beta to the power n, and beta by pi to the power n by 2, because it is a square root here, and then you have n such terms. So, beta by pi to the power n by 2. Then look at the n values of x i's. So, x 1 square into x 2 square into x 3 square etcetera. So, I write that as pi of I is equal to 1 to n x I square, then e to the power minus beta x 1 square plus x 2 square etcetera. So, I write this as e to the power minus summation I is equal to 1 to n beta x I square. So, this in a simple form we write it as 2 to the power n beta to the power, there is a n here and n by 2 here. So, I write it as beta to the power n plus n by 2, then pi to the power minus n by 2 corresponding to this term into the product I is equal to 1 to n, this term remains the same and this term remains the same. This is the likelihood function. Now, we are looking for those values of beta which maximize this likelihood function. Recall that in the last class I mentioned about the log function. The log of a particular argument will have the maximum value at the same value corresponding to that argument, where the argument itself would have had the maximum value. What I mean by that is, log of a function is a monotonic function, and therefore, it will have the maximum value at the same point where the function itself would have the maximum value. Therefore, it is sometimes advantageous to take the log of likelihood and then maximize the logarithm of that function, specifically when you have exponential functions like this. So, we take the log of the likelihood function. From this you write the log of likelihood function as, see, we are looking at this point. So, we are taking the logarithm on both sides. So, we write this as n log 2 plus n by 2 log beta minus n by 2 log pi, because we had a pi of pi to the power minus n by 2 plus logarithm of the product I is equal to 1 to n x I square minus beta I is equal to 1 to n x I square. Beta is the only parameter. So, we differentiate this function log L of beta with respect to beta and equate it to 0. So, when you differentiate with respect to beta, the only terms containing beta will appear here. So, n plus n by 2 by 1 by beta, you are differentiating with respect to beta, minus x I square, summation of x I square, you are again differentiating with respect to beta. Those terms which do not contain beta will vanish from here, and therefore, you get after simplification beta cap is equal to 3 n divided by 2 into summation I is equal to 1 to n x I square. So, essentially what we did is, given a PDF, we formulate the likelihood function for the sample which is realized, which is x 1, x 2, x 3 etcetera x n, and then depending on the nature of the likelihood function, sometimes we take the logarithm of the likelihood function and maximize the logarithm of the likelihood function. In this particular case, we did take the logarithm, and because we are maximizing, we take the first differential, which is a necessary condition, first differential with respect to the parameter, equate it to 0 and solve for that parameter. If you had more than one parameters in this case, what you would have done, you would have differentiated the logarithm of this likelihood function with respect to each of the parameters, and therefore, and thus generating those many equations as you have number of parameters, solve all of them to get those parameters. Now, we come to an interesting result called as the Chebyshev inequality. See, what we did just now is to estimate the parameters. So, we had a probability distribution function given, probability density function given, and then we were estimating the parameters. Now, once we estimate the parameters for a given sample, you have the complete description of the probability density function, and therefore, the CDF, the cumulative distribution function in place, and then you would have talked about various probabilities. So far we have been talking about probabilities associated with a given density function or a distribution function. Now, there will be situations where you will be interested in not so much on the probability of a particular event itself, as in the deviations of that particular random variable, and you do not have information on the probability underlying probability density function or the probability distribution function. So, the Chebyshev inequality, let us first state it and then see the significance of this. The Chebyshev inequality states that a single observation selected at random from any probability distribution will deviate more than k sigma from the mean with a probability less than or equal to 1 by k square. More formally, we write this as probability of the absolute value of x minus mu being greater than or equal to a specified value k sigma, k times sigma, will be less than or equal to 1 by k square. So, here we are interested in what is the maximum probability with which a given value of x will differ from its mean by more than k sigma, let us say more than 1 sigma, 2 sigma, 1.5 sigma, etc. So, we are interested in how far is the deviation, what is the maximum probability by which it will differ from its mean on either side. So, it can be either x minus mu may be positive or x minus mu may be negative. On either side, what is the probability that it will deviate more than k sigma. Now, the Chebyshev inequality places an upper bound on this probability, and that is 1 by k square. Remember, this result is irrespective of the probability distribution, and therefore, it becomes handy when we are when we want to place higher limits or the upper bounds on the probability of this particular deviation, and this becomes quite handy in certain situations. For example, you are talking about the stream flow and you have the mean value, you do not have the information on the probability distribution, and you would be interested in what is the probability that the stream flow will deviate from the mean by 1 sigma, 2 sigma, and so on, and you will be interested in the maximum probability. So, that maximum probability is given by 1 by k square. So, in many situations the Chebyshev inequality becomes is a very handy result to use in applications when you do not have information on the underlying probability distribution itself, but you would be interested in getting the maximum probabilities of the deviations from the mean. Let us look at a simple example where we are considering the mean annual stream flow for river being given as 135 million cubic meters, and its standard deviation is 23.8 million cubic meters. Remember, these values we would have got from the sample. So, we would have estimated the mean to be 135 million cubic meters and the standard deviation to be 23.8 million cubic meters. Now, we will be interested in what is the maximum probability that the flow in a year will deviate more than 45 million cubic meters from the mean. These kind of questions would be of course of practical relevance, because knowing the mean we may be interested in seeing how low the flow can go, or what is the maximum probability that the flow will deviate by 45 million cubic meters from this on either side, because you would like to plan for water resources utilization, the stream flow utilization based on such information. and therefore, you will be interested not so much in the probability density function or the probability distribution functions themselves, but you would be interested in what will be the maximum probability of such an event happening. So, we will use the Chebyshev inequality, which states that probability of the absolute value of the deviation x minus mu being greater than or equal to k sigma will be less than or equal to 1 by k square. So, here we are saying that k sigma is equal to 45, because we are saying what is the maximum probability that the flow in a year will deviate more than 45 million cubic meters. So, we are saying k sigma is equal to 45. So, k into 23.8, which is the sigma standard deviation, will be equal to 45, and therefore, k will be equal to 1.891 in this particular expression, and therefore, we write this as probability of the deviation, the absolute value of the deviation being greater than or equal to 45. I write this as probability of the absolute value of the deviation being greater than or equal to 1.891 sigma, and from the Chebyshev inequality this should be less than or equal to 1 by k square. So, this should be less than or equal to 1 by 1.891 square, which is less than or equal to 0.28, which means we are saying that the probability that the mean annual stream flow, will deviate more than 45 million cubic meters from the mean is less than or equal to 0.28. This is the result that we obtained from the Chebyshev inequality. So, one is specifying a probability density function, obtaining its parameters using any of the three methods that we discussed, and then from the probability density function, which is thus defined completely by estimating the parameters from the sample, you talk about various probabilities. Whereas, the Chebyshev inequality does not bother about the probability distribution from which the sample has been drawn, but you have the estimates of the mean and the standard deviation, from which you talk about the maximum probabilities or the upper bounds on the probabilities of the deviation of x minus mu on either side. Now, we will look at another important topic, where we are discussing about the joint variations of two random variables. In our initial classes, typically the second lecture, we discussed about the joint density function and subsequently the conditional density function and the marginal densities and so on, when we are talking about the two dimensional random vectors. We will now introduce the movements of the two dimensional random vectors with a specific purpose. Recall that the first the nth moment of a single dimensional random variable, we defined this as x minus mu to the power n, that is the integral minus infinity to plus infinity x minus mu to the power n f of x dx. This is the nth moment about mean of the single dimensional random variable, and from this, by putting n is equal to 2, what did we obtain? We obtained the variance. So, sigma square was x minus mu to the power 2 f of x dx. Now, when you have two random variables x and y, which are jointly distributed random variables, with f of x y as the joint PDF. Now, we define analogous to the single dimension random variable, we define the RSth moment of this two dimensional random variable as double integral minus infinity to plus infinity x minus mu x to the power r y minus mu y to the power s f of x y dx dy. So, this is the definition of the RSth moment of a two dimensional random variable, analogous to the nth moment of the single dimensional random variable. When r is equal to 1 and s is equal to 1, we call this moment as the covariance. So, in the case of the single dimensional random variable, when n is equal to 2, we call that as the variance. So, in the case of two dimensional random variables, when r is equal to 1 and s is equal to 1, that is 1/1th moment is what we are talking about, that is defined as the covariance. So, we write the covariance of x and y as double integral minus infinity to plus infinity x minus mu x, y minus mu y, f of x y dx dy. Recall that what is your expected value? Expected value of, let us say I write this as g of x comma y in a two dimensional random variable case. This is nothing but minus infinity to plus infinity the function g of x comma y into the PDF, the joint PDF x f of x y dx dy. This is how we define the expected value of a function. We use that definition and then our function here is x minus mu x into y minus mu y. This is the function of x and y and multiplied by the joint density function f of x y and with respect to dx with respect to x and y, we are integrating that with respect to x and y. So, and therefore, from this result we write this as the expected value of x minus mu x into y minus mu y. So, the covariance of x and y, covariance of x comma y is given by the expected value of x minus mu x into y minus mu y. The covariance is denoted as sigma x y or simply covariance of x comma y. So, this is how we denote the covariance. Remember from your earlier single dimension random variables, we can show that sigma x y is equal to 0 if x and y are independent. How do we show that? Let us say we will come back to this problem, that is we are saying that covariance of x comma y or sigma x y. How did we define this? Sigma x y we defined as minus infinity to plus infinity of x minus mu x, y minus mu y, f of x comma y dx dy. Okay, this is how we defined our covariance. Now, if x and y are independent, that is these are independent random variables, what is the property of stochastic independence? Recall that when x and y are independent, your joint density function f of x y will be equal to the product of the marginal density function, that is g of x into h of y. So, we use this result and then write f of x y is equal to g of x y x into h of y in this expression. So, what do we write? This will be minus infinity to plus infinity, minus infinity to plus infinity, x minus mu x will keep it as it is, y minus mu y will keep it as it is, and in place of f of x y I will write this as g of x into h of y, where g of x is the marginal density of x and h of y is marginal density of y. So, from this see here from this we write this as sigma x y, that is covariance of x comma y, as minus infinity to plus infinity. I will write x minus mu x into g of x dx, y minus mu y h of y dy. Recall that g of x is a function of x alone and h of y is a function of y alone. And therefore, I write this as minus infinity to plus infinity x minus mu x g of x into minus infinity to plus infinity y minus mu y into h of y. This is with respect to x and this is with respect to y. Can you recall this this integral? For example, I will write this as minus infinity to plus infinity x into g x dx. What is x into g x dx? That is mu x itself, minus mu x into integral minus infinity to plus infinity g of x. What is that? Integral minus infinity to plus infinity g of x dx will be equal to 1, because g of x is the probability density function, and therefore, this would be mu x minus mu x itself, that will be equal to 0. Similarly, this will be mu y into mu y itself, that will be 0. So, this will be sigma x y will be equal to 0. So, sigma x y will be equal to 0 if x and y are independent. You must remember, however, that the converse is not in general true. That is, you may have covariance of x comma y as 0, but that does not necessarily mean that x and y are independent. So, we state sigma x y is equal to 0 if x and y are independent. However, the converse may not be necessarily true. And from this, again we write the sample estimate of the covariance is given by x I minus x bar into y I minus y bar by n minus 1. So, you have n values of the observed values of x I and concurrent values of y I. So, you have n values of x I and n values of y I, and in which case you estimate the covariance as given by this expression. For example, you may have rainfall values, let us say annual rainfall values for 50 years, and the concurrent runoff values at a particular location generated by this particular rainfall for the same 50 years. So, you have the 50 values of rainfall which have generated the 50 values of runoff, and then you are relating these two and you are talking about the covariance between rainfall and runoff. So, that is how you estimate from the sample the covariance of this. Now, from the covariance we move on to an important concept called as the correlation. So, the correlation is actually a measure of a degree, the degree of association between two random variables x and y. As you can see from the definition, we define the covariance correlation rho x y as the covariance sigma x y divided by the standard deviation of x multiplied by the standard deviation of y. This is a normalized covariance. So, we are normalizing the covariance sigma x y with respect to the standard deviation of x and standard deviation of y. As you can see, sigma x y had the units of x multiplied by the units of y. If your rainfall was in millimeters and runoff was also in millimeters, then the covariance between covariance of rainfall and runoff would be having units of millimeter square, and the standard deviation of the rainfall x would be in millimeters, standard deviation of y will be in millimeters, and therefore, the rho x y that you get, which is a correlation, is a unitless parameter, and it is thus a normalized covariance. Presently, we will show that rho x y in fact varies between -1 and +1, and rho x y is equal to 0 if x and y are independent, because your sigma x y will be 0 as we just showed. So, sigma x y, which is the covariance between x and y, covariance of x and y will be 0 if x and y are independent, and therefore, the correlation will be 0. remember, if x and y are independent, the correlation coefficient is 0, but often we confuse, if correlation is 0, we often confuse it with x and y being independent. It is not necessarily true. So, the fact that correlation is 0 should not directly imply that x and y are independent. However, if x and y are independent, then correlation will be necessarily 0. So, from this definition, we get the sample estimate of the correlation as R x comma y is equal to the sample estimate of the covariance, which is S x comma y, by the sample estimate of the standard deviation S x and sample estimate of the standard deviation S y. If we have a perfect correlation, that means, if your R is equal to 1 or the rho x y between two variables x and y, the correlation is 1. This indicates that all the values, all the observed values will lie on a perfect straight line. If your correlation is -1, then it will lie on a straight line something like this, which means the higher the values of x, the lower will be the values of y. So, rho x y is positive, indicates that the larger values of x tend to be paired with larger values of y and vice versa. That is, if rho x y is positive, that is, we say the higher the value of x, the higher will be the value of y if rho x y is positive. If rho x y is negative, the higher the value of x, the lower will be the value of y, and therefore, the larger values of x tend to be paired with smaller values of y and vice versa if rho x y is negative. Remember also that the correlation coefficient is a measure of linear dependence. We will show that presently, that the way we have defined rho x y, it indicates the linear dependence between x and y. And that is why in fact, the fact that rho x y is equal to 0 does not necessarily mean that there is a complete independence between x and y. There may be a non-linear dependence between x and y, which the correlation coefficient cannot capture. So, we will take some examples now. You have observed values of x and y, and these are the observed values, let us say, and you have a certain amount of correlation between them. So, there is certain stochastic dependence between these two. So, it indicates that there is a certain linear dependence between x and y. And if you take such a scatter here and you calculate the correlation coefficient, you may get a much lower correlation coefficient corresponding to this. So, points are scattered to a greater extent than they were here, and therefore, there is a smaller correlation coefficient. So, if you try to fit a straight line, for this you may get a better straight line fit compared to this straight line, the straight line that you may fit for this type of scatter, and therefore, the correlation coefficient is much lower compared to the correlation coefficient here. You look at this example here. Now, this is a maybe a parabolic type of these points lie on a parabola, and you get a very high value of correlation R is equal to 0.949. Although the relationship, there is a functional relationship between x and y here, the relationship was non-linear, but you can fit a straight line with much smaller scatter compared to the previous case here. So, you may be able to fit a straight line with a much smaller scatter, and therefore, the correlation which indicates the linear dependence between x and y is much larger in this particular case. You take the case of points which are lying around lying on the periphery of a circle on the circle. So, this is there is a perfect functional relationship between x and y defined by the equation of the circle here. However, the correlation coefficient will be 0 here in this particular case, because there is a non-linear functional relationship and the coefficient the correlation coefficient captures only the linear relationship. So, r will be equal to 0, although there is a perfect functional relationship between x and y. So, the point you must remember is that the correlation coefficient indicates or captures the degree of linear dependence between x and y. We will just see what does correlation coefficient being for a perfectly linear relationship indicate. For this, we will express this covariance of x and y in a slightly more convenient fashion. This is equal to expected value of x minus mu x, y minus mu y. So, this we write it as expected value of x y. We simply simplify this x y minus x into mu y minus y into mu x plus mu x into mu y. So, from this, after you simplify this, you get it as equal to expected value of x y minus expected value of x, expected value of y. So, this is how we express covariance of x comma y, and then we revisit the definition of correlation coefficient. This is rho x y as is defined as sigma x y by sigma x sigma y. Now, we consider a perfectly linear relationship between x and y. Let us say that y is defined as a x plus b, which is a perfect linear relationship. Now, we consider rho x y square, which is the correlation coefficient square. We write this as sigma x y square divided by sigma x square sigma y square. And what is sigma x y? Sigma x y is expected value of x y minus expected value of x, expected value of y, and we are squaring the whole term. And we will retain this sigma x square sigma y square as they are right now, and then substitute y is equal to a x plus b. So, wherever y is there, I will substitute a x plus b and simplify this as expected value of a x square, because y is equal to a x plus b x minus expected value of x and expected value of y here, which is expected value of a x plus b. The denominator will keep it as it is, and then when we simplify this, what do we get? We get a square expected value of x square minus expected value of x the whole square. Can you recognize this term within the bracket? It is in fact sigma x square, which is the variance of x. So, we write this as a square sigma x square the whole square. So, we get a square sigma x to the power 4, and we have sigma y square here, and y is a x plus b. So, when y is a x plus b, you recall that sigma y square is a square into sigma x square, and therefore, we write this this sigma x square and sigma x square gets cancelled here, a square gets cancelled here. So, this turns out to be 1. Therefore, rho is equal to plus or minus 1 if there is a perfect linear relationship, because you got rho square is equal to 1 here. So, we started with rho x y square. So, that turns out to be 1, and therefore, rho is equal to plus or minus 1 if there is a perfect linear relationship between x and y. So, the correlation coefficient is in fact a measure of linear dependence. So, if correlation coefficient has any other value than 1 plus or minus 1, it indicates that there is a lesser degree of linear dependence between x and y compared to the perfect relationship, which would have yielded a correlation coefficient of plus or minus 1. Let us do a simple example now. Let us say you have rainfall at a particular location and the associated runoff. We have 15 observed values, maybe 15 years of observed values. The rainfall values are in centimeters and the runoff values are also in centimeters. This runoff that we are talking about is in fact generated by this rainfall. So, in the first year you have a 105 centimeters of rainfall that has generated 42 centimeters of runoff and so on. Now, we are trying to see what is the relationship, what is the dependence of runoff on rainfall. So, we use the correlation coefficient as a measure of linear dependence and examine how much of dependence exists, how much of linear dependence exists between runoff and rainfall. So, we simply use this expression that we have for the sample estimates of rho x y. This is S x y by S x S y, and how do we estimate S x y? S x y is simply summation of x minus x bar into y minus y bar summed over I is equal to 1 to n divided by n minus 1. This is how we estimate the covariance of x and y. So, we use these expressions and then calculate the correlation coefficient. So, first we obtain the mean, which turns out to be 1627 is the summation, and the mean of rainfall is 108.5, and similarly the variance S x square comes out to be 250 and the standard deviation comes out to be 15.811. Similarly, for y, which is the runoff, we estimate y bar as 38.33 centimeters and the variance as 117.5 centimeter square, and therefore, the S y comes out to be 10.841 centimeters. So, once we have the mean and the standard deviation, we open out columns like this. The rainfall values are given here and the concurrent values of runoff are given here. Then we obtain x I minus x bar and y I minus y bar, x I minus x bar the whole square, y I minus y bar the whole square, and then x I minus x bar into y I minus y bar. So, your x bar was given as 138 or something here, x bar is 108.5 and y bar is 38.33. So, what we do is x minus x bar here and y minus y bar here. Remember, because you are taking the first deviation, it can be negative. So, similarly, here first deviations can be negative. When you square, they will all be positive here. And then you get x I minus x bar, y I minus y bar. So, essentially you are multiplying this term with this term to obtain this term, x I minus x bar, y I minus y bar, you will get this, and this one is x I minus x bar the whole square. So, this term the whole square will give you this term. So, like this you calculate these for all of these terms here until 15 years. So, for all the 15 terms you calculate these and you have the associated sums here. So, all these sums are available on the last row here. Now, this you can do readily on any spreadsheet programs like Microsoft Excel and so on. So, very easily you can do all these calculations and then use these calculations for estimating your covariance first. So, S x y you estimate it as x I minus x bar into y I minus y bar, summation of that, which is available in this column, x I minus x bar, y I minus y bar, which is available in this column by 15 minus 1. So, 1974.67 by 15 minus 1, which turns out to be 141.05. What will be the units of this? This will have units of rainfall into runoff, which means centimeter square. Then from this you estimate the correlation coefficient S x y by S x into S x S y. So, S x y is 141.05 and S x, which is the standard deviation of x, which we have calculated here as 15.811, and similarly standard deviation of y is 10.841. So, we use those values and get the correlation coefficient as 0.823, which is quite a high correlation coefficient, indicating that there is a good linear dependence of runoff on the rainfall, on the associated rainfall. However, how significant is the correlation is a different story altogether. We should explore whether the correlation coefficient that we got just now is in fact statistically significant. That we will study slightly later, but you must remember that the correlation coefficient value let us say 0.8, 0.7, 0.6 etc., when you get correlation coefficient values like this, you should not make a judgment just based on those values, whether there is a strong linear relationship between the two variables that you have considered or not. You must also examine how significant is this correlation coefficient value. For example, in the last example that we numerical example that we considered, we had 15 values and we obtained a correlation coefficient of let us say 0.84 or some such thing. If we had let us say instead of 15 values we had 100 values and we obtained a correlation of 0.53 or some such thing. Can we say that the 0.53 correlation indicates that there is a much lesser linear dependence of y on x compared to the 0.84 or something that you obtained for the 15 values? We will not be able to say this, and that is where we have to check whether the correlation coefficients we just obtained are in fact statistically significant or not. Okay, next we will go on to the next topic, which is which is a continuation of the discussion of correlation, where we are interested in obtaining a linear relationship, let us say between x and y. We have the observed values of let us say rainfall and concurrent values of runoff, or rainfall and let us say groundwater recharge, rainfall and evaporation and so on. So, we have concurrently observed values of two variables and we want to obtain a functional relationship between these two variables. So, what do we have? We have just the observed value. So, we have a scatter point, a scatter plot. So, if you plot x versus y, simply you get a scatter of x versus y. Now, with this scatter, we would like to establish a functional relationship and specifically a linear relationship to begin with between x and y. What is the use of this? Let us say you have 50 observed values of rainfall and the concurrent 50 values of runoff observed. If you can fit a linear relationship between these two, you can use the linear relationship for estimating or predicting the value of runoff for any given value of x, that is the rainfall. So, for a given value of rainfall, we should be able to estimate what will be the value of runoff. So, we can use this functional relationship. How do we obtain this functional relationship? You have the observed values of rainfall and runoff, and we have the scatter point, as you can see from this figure. You have these observed values. So, you have the scatter points like this. Now, we want to obtain a linear relationship between these scatter points. This procedure is called as simple linear regression. Simple because we are considering only two variables, x and y is the dependent variable, x is the independent variable, and therefore, it is a simple regression. Linear because we are fitting a linear relationship between x and y. If you have more independent variables, let us say that y depends on x1, x2, x3 and so on. For example, runoff is y and it depends on rainfall x1, it depends on let us say the temperature x2, it depends on the catchment slope x3 and so on. So, if the dependent variable depends on more than one independent variables, then it is called as a multiple regression. And similarly, if you are fitting a nonlinear relationship, it can be a nonlinear regression, multiple nonlinear regression, simple nonlinear regression and so on. So, first we begin with simple linear regression. What is our purpose? We have these observed values each given by x I, y I. So, these are the actual observed values. So, when you plot them as scatter plots, you will get these black dots. So, these black dots are the observed values, and we want to have the best fit line for which will represent these scattered values. So, if you look at a particular point y I, for a given x I we have the y I which is the observed value, and if you fit this best fit line you would have predicted the point to be at this location, and this we denote it as y I cap. So, y I cap is the predicted value, y I is your observed value. So, like this for every value you have the observed value as well as the associated predicted value. Predicted value is on the line which you would have used to predict that. So, y I cap is the predicted value of x I, and we write y I cap as a plus b x I because we are fitting a straight line. So, we will write this as a plus b x I. What is the error? Your actual observed value is y I, but your predicted value is y I cap. Therefore, error E I for the point x I y I is given by y I minus y I cap. So, there are two parameters here a plus a and b. So, once we estimate these parameters a and b, your straight line is completely defined. We want to estimate this line such that the error or the sum of the squared errors is a minimum. That is, over all these observed points, the sum of the squared errors should be minimum. So, we will consider the sum of the squared errors I is equal to 1 to n, the error square, which is y I minus y I cap square, and that we define it as y I minus y I cap is a plus b x I the whole square, and we simplify that. We are interested in getting those parameters a and b which will minimize this sum of square errors. So, we are looking at that particular straight line which will minimize the sum of square errors. So, we take the differential with respect to a and b both of this sum squared errors m, and simplify that. We first get a is equal to y bar minus b x bar. You get a sigma y I term here and sigma x I term here and divided by n. So, you get a is equal to y bar minus b x bar. Similarly, you differentiate with respect to b now, dm by db is equal to 0. You get this expression, all the details are here, it is a simple arithmetic here, and then you get this term, but we write this in a slightly more elegant form by taking x I minus x bar, which is the deviation of this particular point x I from its mean x bar as x I dash, and y I minus y bar we write it as y I dash. Using this we write the expression for b in a more elegant form as this is all of this will give you the simplification. What we said is x I minus x bar is equal to x I dash and y I minus y bar is equal to y I dash. So, we consider this x I dash y I dash, which is x I minus x bar y I minus y bar, summation of that, and that can be written as summation of x I y I minus summation x I summation y I by n, which means essentially we are writing this is equal to this expression. And then we write this summation x I dash square, which is nothing but sigma of x I minus x bar the whole square, that turns out to be sigma of x I bar square minus sigma x I the whole square by n. Using these two expressions, we write b in a more useful and more elegant form as sigma x I dash y I dash divided by sigma x I dash the whole square. What is x I dash? X I dash is simply x I minus x bar, that is the deviation of x I minus its mean. Y I dash is deviation of y I from its mean, and x I dash square. So, you can get b. Once you get b, you can get a from this expression y bar minus b x bar. So, b you obtain from the relationship that we just discussed, and from that you know y bar, which is the mean of y, and you know x bar, and therefore, you get a. Once you get a and b, your relationship is completely defined, y I bar is equal to a plus b x I. So, this is how we obtain the best fit line for a scatter of points. We will revisit the example that we just did, in which we calculated the covariance and the correlation coefficient. We will take the same example, because all the columns are available now with us. So, we obtained x bar is equal to 108.5 and y bar is equal to 38.33. Look at this columns here. So, you got x I minus x bar into y I minus y bar. You got also x I minus x bar. What is x I minus x bar in our notation now? It is x I dash. Similarly, this is y I dash, and the summations are available at the end. So, we get sigma of x I dash into y I dash, which is available in this column x I dash y I dash, which is 1974.67, and similarly x I dash the whole square. So, summation x I dash the whole square, which is available from this column x I minus x bar the whole square. So, from this you get first b turns out to be 0.56423, and then from once you get b, you get a, which is y bar minus b x bar, which turns out to be minus 22.889, and therefore, y is equal to a plus b x, which is 0.564, which is b x minus 22.895. So, you defined the line completely now by using the data that was available with you, and thus you are able to say that for a given x, my predicted value of y will be as given by that line. So, you specify any value of x, you should be able to get the value of y. Now, these can be used for several occasions. That means, you have observed the values, and from the observed values you are converting the observed values into a mathematical model, which is a simple straight line, and then you can use this straight line to represent the runoff for that location. Then you will be able to answer several questions. If my rainfall is so much, what will be my runoff, and so on. And this can also be used to some extent for data extension. That is, if you have 50 years of data, then you can extend it to let us say 60 years or 70 years using this particular relationship. Of course, there are other issues involved there, the issues concerned with outliers and so on. Will at this point of time, we will not worry too much about this. So, in this lecture, we have we started with the method of maximum likelihood. We solved one example, and then we stated the Chebyshev inequality, which places an upper bound on the deviations of a particular random variable from its mean. Then we went on to define the covariance between two variables and defined the correlation coefficient, which is in fact a linear, which is in fact a measure of linear dependence between x and y. And from that we moved on to simple linear regression, where we define a straight line between the variables y and x. Y is a dependent variable and x is the independent variable. So, we will continue this discussion in the next lecture. Thank you for your attention.